Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to the subject Electromagnetic Field Theory. We are with chapter number 11, that is plane wave reflection and dispersion. In the previous chapter we have seen the wave propagation through different kind of mediums, and now in this chapter we are seeing the reflection of uniform plane wave at some boundary interface. So very first of all we started with the first topic, reflection of uniform plane wave from the boundary interface which separates out two general mediums. So the mediums were characterized by the conductivity sigma, the permeability mu, and permittivity of the medium represented by epsilon. So thereupon, on to considering the medium number 2, the perfect dielectric, we have solved 3 problems. Now we followed the topic, the reflection of electromagnetic wave from a perfect conductor at normal incidence. For both the cases we have taken normal incidence, and lastly we have seen the standing wave ratio. Based upon to the formula of standing wave ratio and reflection coefficient in terms of each other, we have solved one problem also. Let us take second problem. So here we have the problem statement. The semi-infinite regions z less than 0, z greater than 1 meter are free space. For z ranging from 0 to 1 meter, we have epsilon r equal to 4, mu r equal to 1, and sigma equal to 0. A uniform plane wave with omega is equal to 4 into 10 raised to power 8 radians per second is traveling in the az cap direction towards the interface at z equal to 0. So here we have two parts. In part A, find the standing wave ratio in each of the 3 regions, and in part B, find the location of maximum capital E bar magnitude for z less than 0, that is nearest to z equal to 0. So to read this problem statement, we come to know the regions are multiple: less than 0, greater than 1, and the region between 0 to 1 meter. So here first of all into the diagram we show these 3 regions. If this is the z measurement, so upon this z measurement we shall mark first of all z equal to 0. So this is the marking z equal to 0. Therefore this will be the region number 1, that is z less than 0. We have another marking, that is z equal to 1. So this is that marking z equal to 1. Hence the second region generally we take onto the right hand side. This will be z greater than 1 meter. Now we get back to the problem statement. As per the problem statement, these two regions z less than 0 and z greater than 1 meter are semi-infinite regions. So infinity for this particular region is onto the left hand side, and infinity for this particular region is onto the right hand side. So this is the positive side of z, and this one is the negative side of z. So this is the place of origin, we can say z equal to 0, or in another words we can say this is the plane xy plane. Now in this particular region, that is in between these two semi-infinite ones, z ranging from 0 to 1 meter, we have epsilon r 4, mu r equal to 1, and sigma equal to 0. So in this particular region we write the values sigma 0, epsilon r equal to 4, and mu r is equal to 1. So now a uniform plane wave with omega equal to the angular frequency 4 into 10 raised to power 8 radians per second is traveling in az cap direction towards the interface at z equal to 0. So z equal to 0 interface is here. So we can imagine this is the traveling wave. The traveling wave is always into the medium number 1. So here it has the angular frequency given by 4 into 10 raised to the power 8 radians per second. Now the direction we have shown, that is positive az cap direction. Now in part A, find the standing wave ratio in each of these 3 regions. So for, let us say this is region number 1, characterized by Z less than 0. This is region number 2, and this one is region number 3. So corresponding standing wave ratio for region 1, we can give the symbol S suffix 1, for the region 2 S suffix 2, and for the region 3 that is S suffix 3. So what are the standing wave ratios into these regions is part A, and in part B find the location of maximum E bar for Z less than 0, that is nearest to Z equal to 0. So we have seen that if a certain traveling wave incidents onto the boundary interface that separates two particular regions, so a part is transmitted further and another part is reflected. So for the reflected portion, we see because of the presence of traveling as well as the reflected wave, we have the standing wave, and that standing wave is having the maxima and minima values. So this is the maxima, this is the minima. So right from Z equal to 0 interface, which is the maximum position, so that position in terms of Z we have to give the location of maximum for the magnitude of electric field intensity. So let us begin to solve part A here. So for part A we have, so for part A we have here omega given by 4 into 10 raised to power 8, 4 into 10 raised to power 8 radians per second. We want the standing wave ratio. Now first of all we take the phase shift constant into the second region. So second region is this one. For this particular region we have beta suffix 2. So beta suffix 2 will be equal to, according to the formula, we have omega under root of epsilon r2 divided by c. So from the formula of velocity of propagation, we have the phase shift constant in terms of the angular frequency, relative permittivity, and the velocity of propagation into the free space. So omega is 4 into 10 raised to power 8, we substitute. Relative permittivity for medium number 2 or region 2 is equal to 4, hence it will be under root 4, and here we have the magnitude 3 into 10 raised to power 8 meter per second, giving us the value under root 4 is equal to 2. 2 into 4 will be 8. 8 divided by 3. So 8 divided by 3 is equal to 2.67. So as beta is phase shift constant, so it is always measured in terms of radians per meter. So beta, that is phase information for region 2, that we have obtained right now. So using this particular information, if we multiply this particular beta by the length into this region 2, let us say d is the length into this region 2, we have the location that is z equal to 0, z equal to 1, hence d will be equal to 1 meter. So in symbol form we write beta 2 into d, so this is equal to 2.67 radians per meter in multiplication with 1 meter, giving us beta 2 into d is equal to 2.67 radians of phase change into the medium number 2. Now if we give the designation of eta 2 for the intrinsic impedance into the medium number 2, so it will be given by, we have the formula under root mu divided by epsilon. So if mu is equal to mu 0, because we have mu r equal to 1, epsilon r is equal to 4, so this shall become mu 0 divided by 4 times epsilon 0, giving us eta 2. Under root mu 0 upon epsilon 0 we can write eta 2. So this will be eta 0 divided by under root 1 by 4 will be 1 by 2. Hence eta 2 is nothing but eta 0 divided by 2. Now from this particular intrinsic impedance we try to determine the value of input impedance. So input impedance can be given the notation eta suffix in, and it will be given eta 2 in the bracket Here we have eta 0 cosine of beta 2d plus j times eta 2 of, it is sine of beta 2d divided by, here it is eta 2 cosine of beta 2d plus j times eta 0 sine of beta 2 into d. So if we substitute the value, eta 2 is equal to eta 0 upon 2, so this is 377, or we can put 125 divided by 2. We substitute, this is equal to twice cosine of 2.67 plus j sine of 2.67 upon cosine of 2.67 plus j 2 times sine of 2.67. So this is equal to 231 plus j times 141 into the complex form. This is the input impedance. So knowing the input impedance, the reflection coefficient at that particular interface, we can mention, let us say the reflection coefficient we mention by the suffix 1 2, as we have the two kinds of interfaces. So for region 1 and region 2 interface, the reflection coefficient we denote by gamma suffix 1 2. For 2 to 3, we can have gamma suffix 2 3. So gamma suffix 1 2, the reflection coefficient in terms of the intrinsic impedances, it will be input impedance minus eta 0 divided by input impedance plus eta 0. So eta 0 is for the free space, that is region 1 and region 3 as per the problem statement. As per the problem statement, the semi-infinite regions z less than 0 and z greater than 1 meter are free spaces. So this is free space. This is also free space that we require to represent here. Hence sigma equal to 0, epsilon equal to epsilon 0 and mu 0. Here also epsilon 0, mu 0, sigma equal to 0. So therefore, substituting the values of input impedances and eta 0 into this particular formula, we obtain 231 plus j times 141 minus 377 for eta 0 value. This is 231 plus j times 141 plus 377. So this we shall obtain minus 0.176 plus j times 0.273 is equal to, into the polar form if we change, so this is 0.325 angle 123 degrees. So now we have reflection coefficient at the first interface, that is the interface which separates region 1 from region 2 at z equal to 0 plane. So knowing the reflection coefficient, we can find the standing wave ratio, because as per the problem statement we require standing wave ratio at each of the three regions. Therefore, the standing wave ratio in terms of the reflection coefficients we can mention by the formula. For the first region S1, we shall be writing it is 1 plus mod of the reflection coefficient for the interface between 1 to region divided by 1 minus, it is gamma suffix 1 2. Therefore, we have the reflection coefficient magnitude. Therefore, 1 plus 0.325 divided by 1 minus 0.325 will give us the reflection, the standing wave ratio. So this calculation gives us the value, it is 1.96. So 1.96 is the required standing wave ratio for region number 1. So for part A, we are covered for region number 1. Now for region number 2, we shall require the similar kind of reflection coefficient between the for the interface between the region 2 and region 3. So thereupon we shall denote the reflection coefficient with gamma suffix 2 3. So gamma suffix 2 3 for region 2 to 3 will be given in terms of intrinsic impedances eta 0 minus the input impedance or the intrinsic impedance for the middle region, we can substitute eta 0 divided by 2 divided by eta 0 plus the addition eta 0 divided by 2. So this shall give us 1 minus 1 divided by 2 upon 1 plus 1 divided by 2. So simply we can make this reflection coefficient gamma suffix 2 3 is equal to 1 by 3. So knowing the reflection coefficient, we can write the standing wave ratio S2 1 plus the magnitude of this reflection coefficient is 1 upon 3 upon 1 minus again 1 upon 3. So this calculation gives us S2, that is the standing wave ratio in region number 2 is equal to 2. So for part A, we have calculated standing wave ratio for region 2 also. So here it is the answer, that is 2. Now we require the standing wave ratio for the third region. So for third region, since there is no reflected wave, because if you get back to the diagram here, in the diagram we have the three regions separated. So in this diagram we are considering the transmission from the first interface only, no reflection at the region number 3. So there won't be any reflected wave for region number 3. Therefore the standing wave ratio for the region 3, we shall write S3 is equal to 1, since no reflected wave exists into this particular region. Hence for part A, for region number 1, we have the reflection coefficient 1.96. For region 2, the standing wave ratio 1.96 for region 1. For region 2 it is 2, and for region 3 it is equal to 1. Therefore we are covered with part A. Now for part B, we require the location of maximum E bar for Z less than 0, that is nearest to the Z equal to 0. So in that case, we take the region that is Z less than 0 and we require the location that is nearest to Z equal to 0. So here we have the reflection coefficient, that is gamma suffix 1 2, and the phase for this particular reflection coefficient was obtained to be 1 2 3 degrees. The magnitude that we have utilized to determine the standing wave ratio in previous part. The phase is important here. So in terms of radians, if you convert these 123 degrees, it will be 2.15 radians. 2.15 radians. So therefore, for the maxima, we have the Z max formula, that is minus pi divided by twice beta. So in the numerator, we shall write this minus 2.15, and into the denominator we have 2, and initially we had calculated the beta for the region, so it is equal to 4 divided by 3. So this gives us the value minus, it is 0.81 we can approximate, as it is the distance to obtain the maxima, we write meters as the unit. So this is the required answer for part B. So the location of maximum magnitude of electric field intensity vector for Z less than 0 region, that is region 1, nearest to the interface at Z equal to 0 is having this answer, that is minus 0.81 meters. So with this answer we are covered with part A and part B. So I hope you have understood the standing wave ratio, its significance, along with the use of reflection coefficient to calculate it. In the next video, we shall be going to take the new topic, that is the plane wave reflection from the multiple interfaces. So in this problem, actually we had the two interfaces. So if such multiple interfaces are there, so how can the reflection of uniform plane wave at every interface can be thought about? So let us see into the next topic. For such more topics and more information about this subject, electromagnetic field theory, you can subscribe to Ekeeda channel. Thank you.